And I'm going to change the numbers to protect the innocent. The demand function is given by P equal to 20 over 1 plus 0.02x, where x is greater than or equal to 0. Where P is the price, and x is the number of units. And then it asks a couple questions. So the first question is to find x as a function of P. The second question is to find the number of units sold when the price is $10, which requires us to do the first part first. So I want to find x as a function of P. So if I'm trying to essentially take this equation and solve for x, my first step is probably going to be to multiply both sides by this denominator. So I'm going to rewrite this as P times 1 plus 0.02x equal to 20. Then I'm going to distribute this P. So I have P times 1 plus P times 0.02x equal to 20. And now my goal is to isolate x. So I'm going to leave this on this side, but I'm going to subtract P. So I have P times 0.02x equal to 20 minus P. And I'm going to divide both sides by P and by 0.02. So I'm going to get x equal to 20 minus P divided by 0.02 P. We could probably simplify this, but I don't really think we need to unless WebAssign wants you to. So that's how you would solve for x as a function of P, or a number of units as a function of price. And then the second part, which is to find the number of units when the price is $10. So then we're just going to set price equal to $10, not $100, $10, and plug that in. So if I plug that in, I'm going to get x equal to 20 minus 10 over 0.02 times 10. And that's going to equal to 20 minus 10 is 10. 0.02 times 10 is 0.2. And 10 divided by 0.2 is like 100 divided by 2, which is 50. So that's how we do a problem like that. And hopefully, I don't remember who asked me to go over that, but hopefully whoever asked that is here, and that's helpful. The other question they asked, I think, is, well, it's definitely leading much more towards what I want to talk about today, which is limits. Limits, super important. The following question is, again, I'm going to change the numbers just a little bit. Let's say we have f of x equal to the square root of x plus 7 minus the square root of 7. That's a 7 on an x. All over x. Yeah. Which are not the letters I would probably use, but whatever. And first of all, I will point out, you might notice that if you try to plug in 0, you're going to get 0 over 0. You're going to get the square root of 7 minus the square root of 7 all over 0. Just 0 over 0, and that's undefined, indeterminate, to be more specific. So this particular question is asking us to actually estimate the following. It's asking us to find what f of 0.1 is, f of 0.01, f of 0.001, and also the negatives. F of negative 0.1, f of negative 0.01, f of negative 0.001. With the intention that finding what these look like they're getting closer to, I think rounded to 4 decimal places, should give us an idea of how to guess what actually this is getting closer to. So really, we're talking about this so that we can then make a guess at what the limit as x approaches 0 of this expression actually is. Now, here's what I want to say. I really, really, really do not want to get out a calculator and make this calculation 6 times. It seems really annoying. Also, it seems really like not great use of our time. So here's what I'm going to show you. So normally what I would have done in years ago before Desmos, I would have gotten out my graphing calculator I would have graphed this thing, and then I would have gone to the table on my graphing calculator to find these values. So that's actually what we're going to do here. Let me show you guys. Let me grab Desmos. Yeah. Oh, sometimes. So let me show you guys this, because I think it's pretty neat what you can do here. I think actually more than being neat, it's pretty time saving, which is actually what's valid. So yeah, I don't need this problem anymore. So if we go to the graphing calculator, so I'm just going to graph f of x equal to, I'm going to do this one. So sure, square root, whoops, sqrt is what you need for the square root of x plus 7 minus the square root of 7. And I probably need to throw some parentheses around this before I do the division to make sure it all ends up in the numerator. Sometimes Desmos can be a little tricky that way. Yeah, there we go. I might delete those afterwards because you don't really need those parentheses, whatever. So there we have it. There's our square root of x plus 7 minus square root of 7 over x. Now I can see that as we get close to 0, let's zoom in a tiny bit here, right? It looks like our values are almost 0.189. 0.189. So I would make a guess that's at 0.189. And at 0, it's totally undefined. Now, to actually answer the questions we're being asked, which are to find this thing f of 0.1, f of 0.01, f of 0.001, instead of having to put that in the calculator 6 times, we can do this. We can, I think we hit this thing here. No, yeah, hit that. So you hit the little gear thing, and then convert to a table. And then you can plug in all the values you want. So 0.1, 0.01, 0.001, and I'm hitting return every time, and then negative 0.1, negative 0.01, negative 0.001. And then we can delete the rest of these. So that's really kind of helpful, right? So I can see that f of 0.1 is approximately 0.1883. And f of 0.01 is 0.1889. Actually, I guess I should, no, that's fine. And then f of 0.001 is 0.18897. So I should actually round that up to 0.1890. And then for these other values, right, for negative 0.1, it's, I kind of didn't leave myself enough room here. So for negative 0.1 is 0.1897 is what we need to round to. And then for negative 0.01 is 0.1890. And then for negative 0.001, it's negative 0.18898. So again, 1890. So I would say that it looks like it's getting closer and closer to 0.1890. Now that's probably not exactly the value, but it's a good guess. So I would guess that this limit is equal to 0.1890. But what I really want to say is, how do we actually calculate this limit? With it? So this would be the answer I would give for that question if 7 was the number. But if I actually want to find this limit, there is stuff we can do. And that's kind of where we're going to go today. So dealing with 0 over 0 limits, because most of the time when we have an indeterminate limit, it's often going to be a 0 over 0. There's other types. There's also infinity over infinity, which we will talk about at some point. So let's say I want to find the limit as x goes to 0 of the thing I just did, the square root of x plus 7. Oh, I was trying to omit the person. There we go. Minus the square root of 7 all over x. And the first thing you should always do when you have a limit, or at least I think, is try plugging in what x is approaching, which is called the direct substitution property. Typically, if you can plug in whatever you're approaching here and get a real number out, that's your answer. Not 100% of the time, but most of the time. If we plug in 0 here, though, as we saw before, you get 0 over 0. So what are we going to do? Well, we're going to use some of our algebraic methods. One of our methods, which I think we saw last class, but I'm not positive because I've talked about it in a couple classes, is to multiply by the conjugate. So we're going to multiply the top by the square root of x plus 7 plus the square root of 7, and the bottom by the same thing. Right, because we're really only allowed to multiply by 1. So the things that actually are conjugates we multiply out. So this ends up equaling, so I'm going to make a tiny mistake here that's not a huge deal, but then I'll correct it. So this is equal to, let's see, square root of x plus 7 times square root of x plus 7 is x plus 7. We could write the middle terms, but I want you guys to know that the middle terms cancel. So this times this is x plus 7, and this times this, and this times this cancel each other out. Right? This is square root of x plus 7 times square root of 7. This is negative square root of x plus 7 times square root of 7. Those cancel. That's why we multiply by the conjugate. And then finally, minus square root of 7 times square root of 7 is going to be minus 7. Divided by, we don't multiply at the bottom. Because our goal here, and typically the goal when you're trying to evaluate a limit, is to get rid of the factor in the denominator that is making it be 0. In this case, it's just x, right? X is 0, dividing by 0 is a problem. We would like that x to cancel out. Now, the thing I've forgotten here is the limit. So every step we have to write the limit until we actually get to a place where we can plug in x going to 0. So if you look at the numerator here, x plus 7 minus 7, the 7's cancel. So write this as the limit as x goes to 0 of just x over x times the square root of x plus 7 plus the square root of 7. The x's cancel. And now we can say that this is equal to the limit as x goes to 0 of 1 over the square root of x plus 7 plus the square root of 7. Now we can actually plug in 0, right? If we plug in 0 now, we don't have something that's undefined. We're going to get 1 over the square root of 0 plus 7 plus the square root of 7. So that's going to be 1 over square root of 7 plus square root of 7 is 2 times the square root of 7. So that would be our actual answer. And I'm sure if you plug that into a calculator, it'd be approximately 0.1890. I'm going to check just to be sure. But let's see, 1 divided by 2 times the square root of 7. Oh, don't be dumb, calculator. I love when my calculator just gives me the same expression back, because it's like, this is your exact answer. It gave me the square root of 7 over 14, and the decimal approximation of that is 0.18898. So yeah, our answer of 0.1890, right, rounded to the fourth decimal place, is correct. Kind of cool. But what I really want you guys to take away from this example, at least, is I would definitely, and I would encourage you to use Desmos to calculate all these things in a table instead of calculating each one of them by hand with a calculator. It seems way less annoying to do it this with Desmos. All right, let me grab the other thing I was going to grab. So let's talk more about how to evaluate limits. And really, this would be a day I would love to have a lot more board space. So over on like that side of the room, I could say, there's our list of things that we do. So we'll make a list. We'll maybe I'll make a small list over here. So evaluating limits. First thing you're going to do, you're going to plug it in. So for example, if I was trying to find the limit as x approaches 3 of x squared plus 9 over x squared minus 4x minus 3, minus 3. I might get wrapped up in my head and start thinking, well, maybe this factors, maybe some stuff cancels. I don't think anything actually factors here. And I don't even want to bother thinking about it, because what I want to do first is I just want to see, can I plug in 3? If I plug in 3, I get 9 plus 9 over 9 minus 12 minus 3. Right? Maybe it looked like an x minus 3 was going to factor there. It doesn't. So what do I get here? I get 18 divided by 9 minus 12 is negative 3, minus another 3 is negative 6. So I end up getting negative 3. That's it. That's how we evaluate the limit. There's nothing else to be done here. So the very first thing you want to think about when you're trying to evaluate the limit is just plug it in. Plug in what x is approaching. And if you get a real number, that is 99% of the time your answer. The only time it's not your answer is if you've got some weird like piecewise function where someone's trying to do something kind of tricky. But if you plug it in and get a real number out, that's usually your answer. And that's usually not going to work because people usually are trying to make it a little bit more challenging. So let's take a look at something like this. The limit, this x approaches, what do I got here? -2, oh, that's a good problem, of x cubed plus 8 over 4x squared plus 5x minus 6. Let me double check that is actually what I wanted. Yeah, that works. Okay. So sometimes I forget my own lesson, but we should always at least, if not actually writing it down, we should at least mentally check that if you plug in what x is approaching, you don't just get a real number, right? Because maybe I'm going to miss that. So if I plug in -2 here, -2 cubed is -8, -8 plus 8 is 0. If I plug in -2 here, I get 4 times 4, which is 16, minus 10 minus 6, which is -16. So here I do get a 0 over 0, which means it's undefined. So it's good to at least check, oh yeah, that's a 0 over 0 type. So it means we need to do something else. And in this case, and often the case, the something else we need to do is to factor. So here's what I'm thinking. I know that if plugging in -2 gives me a 0 in the numerator and the denominator, I'm thinking that x plus 2 is going to be a factor, right? Otherwise, plugging in -2 wouldn't really make each of these polynomials equal to 0. It's actually the fundamental theorem of algebra that if you plug in a number like this, or sorry, fundamental, yeah, of algebra, that if you plug in a value and you get 0, x minus that value is a factor. So I'm going to write this as the limit as x approaches -2. All right, so I'm pretty sure an x plus 2 factors on top, or factors out. So I'm going to have x plus 2 times something else. On the bottom, the same thing, x plus 2 times something else. So this is actually kind of useful in that if I know that x minus -2 is a factor, at least in the denominator, I can figure out the rest pretty easily. If x plus 2 is a factor and that's quadratic, I know the other factor has to be, I need an x times a 4x to end up with 4x squared. And I need a 2 times a -3 to end up with a -6. And then I can check to make sure the middle term works. The middle term is 8x minus 3x, which is going to be 5x. So that totally works. The top's a little more challenging. Let me go to the other side for just a second. I imagine many of you have seen this, but maybe not all of you. So if you're trying to factor a difference or sum of cubes, there's an acronym for that. So a cubed minus b cubed, or a cubed plus b cubed. I'm going to write it like this. I'm not filling in the signs just yet, but just wait a minute. Okay, so here's how this works. If you're factoring a cubed minus b cubed or a cubed plus b cubed, it's going to factor like this. You're going to get an a something b times a squared something ab something b squared. And the acronym is SOAP. So the first sign is the same as that sign. The second sign is the opposite of those signs. So here it's a plus, here it's a minus. And the third sign is always positive. I suppose technically it ignores what the sign at the end is, but that's going to be positive too. So there's a way to remember how to factor a difference of cubes or a sum of cubes. So in this case, we're trying to factor x cubed plus 2 cubed. So that's going to be x plus 2 times x squared minus 2x plus 2 squared. A plus b times a squared minus AB plus B squared. A plus B times A squared minus AB plus B squared. That's how it's working out there. And now we can cancel those. Personally, I like to write another line just doing the limit of this, but since I'm kind of out of room, I might just plug it in here and get, all right, if I plug in -2 to the top, I'm going to get -2 squared is 4, minus 2 times -2 is plus 4, plus 2 squared is 4, over, plug in -2 here, I get -8 minus 3. So my answer ends up being 12 over -11, or -12 11ths. So one of the things, which I'm going to put in the broad category of do some algebra, the first kind of algebraic thing we always look for is, can we just factor and cancel? That is often something that's totally going to work. Let's look at a couple more examples. Let's see what I've got here. What else do I have? Sure, why not? Let's look at the limit as x approaches 3 of x cubed minus 9x over x squared minus 4x plus 7. And let's do a mental check together. If we plug in 3, do we get 0 over 0 or do we not? Let's see. I don't think we do get 0 over 0. Let's check. So I plug in 3, I get 27 minus 27. If I plug in 3 on the bottom, I get 9 minus 12 plus 7. That's not 0 over 0. That's 0 over 4. 4? Yeah, 4. And 0 divided by not 0, 0. So sometimes people will try to trick you, for lack of a better word. Right? They'll try to make you think it's maybe going to be a 0 over 0, but it's really not. So you should always do the checking of like, if I plug in 0, or sorry, if I plug in what x is approaching, what do I get? In this case, that's my answer. I'm done. Limit 0. Let's change the problem just a tiny bit. Let's make it the limit as x approaches 3 of x cubed minus 9x over, what do I want on the bottom? Sure. X squared minus 7x plus 12. So I will tell you this is a 0 over 0. Clearly the top is going to 0. The denominator is also going to 0. If I plug in 3 for x, I get 9 minus 21 plus 12, which is 0. So I want you guys to work on this. I'm going to give you a minute and a half to work on this. And I definitely have a stopwatch around here somewhere. I still got my phone. I'm going to give you 90 whole seconds. Work on that problem, see what you get. Always positive, Marshall. That's what the last 2 letters of sub stood for. So you have this last one here is always positive. All right, it's been 90 seconds. So hopefully everybody found an answer. I want everybody to type their answer in the, so I want everyone to type their answer but not submit it yet. I give you 5 seconds. 1, 2, 3, 4, 5. And now everybody submit your answer in the chat. Did I give a dumb problem? It started with, okay, I'm seeing a lot of 0 over zeros. So it definitely starts off 0 over 0, but I think it becomes something that exists. Let's find out together. So maybe I thought of a problem that did exist, but sometimes I come up with weird problems. So let's take a look. I'm going to factor, right? Factor and cancel. So from the top, I can definitely factor out an x. So I get x times x squared minus 9 over x. So on the bottom, I can factor as x minus 4 times x minus 3. Right? I think that's right. Looks right. And then I can factor the top further as x times x minus 3 times x plus 3 over x minus 3 times x minus 4. The x minus 3's cancel. And then I can write this as the limit as x approaches 3 of x times x plus 3 over x minus 4. And now if I plug in 3, I'm going to get 3 times 3 plus 3 over 3 minus 4. Notice that when I plug in the 3, I no longer write the limit, but I have to write the limit every step of the way until I get to the step where I'm plugging in when x is approaching. And then let's see, 3 times 6 is 18, and 3 minus 4 is negative 1. So it looks like the limit's going to be negative 18. All right, let's do some more. It's good to practice. Thank you everybody for responding. I might ask you to do it again. I think it's good to see where all you guys are at, even if you happen to get not the right answer. That is perfectly okay. We're here to learn things, right? So don't be discouraged if you wrote the wrong thing in the chat. Everybody did. That's perfectly fine. I want to know what you guys know. Let's look at another one here. Let's look at the limit. What time is it? Okay, we got lots of time. Let's do one more. So limit as x, well, not just one more, just do the next one. Limit as x approaches negative 5 of, 25 minus x squared over, sure, why not? Why not? Because I said so. 125 plus x cubed. Right. So once again, we have a 0 over 0 type of limit. Now the thing is, here's what you should really take to heart. When you have a 0 over 0, that doesn't mean that's where you stop. That means you have to do more work. There is almost always work to be done so that we can actually get a number. On very rare occasions, a 0 over 0 limit is going to not exist for some reason, but most of the time, if you have a 0 over 0 type of limit, you're going to get an actual answer with a real number. So let's see what this is equal to. Something I've noticed a lot of people do is that when they are factoring something like 25 minus x squared, they really like to write it as negative x squared plus 25. I really don't. I really like to have the positive thing first and the not positive thing second. I might rewrite this just to kind of see what's going to happen. That this is going to be 5 squared minus x squared. And you could rewrite this one, I guess, right? This is x cubed plus 5 cubed to kind of see how things are going to factor. So, and it is a 0 over 0 type, right? I think I already said that. Let me say it again. So the top is going to factor as 5 minus x times 5 plus x, right? Difference of squares factors is the first thing minus the second thing times the first thing plus the second thing. And then a sum of cubes, we just talked about this, right? X cubed plus 5 cubed should factor as x plus 5, right? The s's are the same. And then x squared minus 5x, right? Minus because it's the opposite side. And then the last one is always positive. And then what cancels here? Two things that don't exactly look the same. The 5 plus x and the x plus 5 are the same, right? The order of addition doesn't matter. Order of subtraction does, right? If you were having 5 minus x and x minus 5, those wouldn't exactly cancel each other out. They would leave behind a -1. But here, we're totally fine. And then we're going to, now that we have canceled the things that were making the top and the bottom 0, we're going to plug in the -5 to the rest of the x's. So I'm going to get 5 minus -5 over -5 squared minus 5 times -5 plus 5 squared, which is going to be 10 on top over 25 plus 25 plus 25, which is 75. And you could reduce this. You could factor a 5 from both parts and get, I think, 2 over 15. That's what that reduces to. Something else you might want to see, because maybe you're not sure. In fact, like, let's actually go back to the previous problem for just 1 second, because I want to kind of show you guys, if you were given this and you really weren't sure what the answer was, and you didn't want to just like, I mean, obviously, right, the internet is a vast resource. There are lots of ways to find answers. Any published textbook probably has all the solutions to all the questions available somewhere. But if you actually wanted to like learn a thing without just finding the answer, what I would really think about or encourage you guys to look at is actually kind of graphing something like this using my favorite graphing tool, Desmos. I'm not trying to plug Desmos all the time. It's the best thing we've got, really. So if I plugged in that function, it's going to work out right. So the problem is when you write the numerator and then you do divided by, it usually just gives, right, if you write the whole thing, which is always a problem. So I often start just saying, I'm going to do x cubed divided by, and I'll go back and add on more things to the top, minus 9x over x squared minus 4x plus 7. Let's kind of recenter ourselves here. So there's our function. And I'm specifically interested in what's happening near 3. So you could just zoom in and see what's happening at 3. It looks pretty defined around 3. Is it really equal to 0? Did we end up getting, did I write the wrong? Oh, I wrote the wrong. Well, yeah. So it is 0 because I'm writing that function whose limit is totally 0. Let's actually write the one that was undefined at 3. So let's change that to the bottom was x squared minus 7x plus 12. Sorry about that. Okay, let's recenter ourselves. So if we look here near 3, sorry, so I can click away. There's a lot of ways you can kind of figure out what's happening near a point. I kind of like just this method of of making everyone have vertigo. So near 3, it certainly looks like the values are pretty close to -18. Right, here's a little bit less than 3. Here's a little bit bigger than 3. It's looking like -18. You could also do the thing where you give yourself a table and you can be like, what's happening at 2.99999? And what's happening at 3.0001? That's giving me a very strong indication that at 3, the limit would be -18. So if you're really not sure about a thing and you don't know like how to kind of manipulate it, look at the graph, because the graph, even if it's not like going to help you show the work, it's going to give you an idea of does the limit actually exist or not, even though the function is totally undefined in 3, right? You look at 3 here, oh, that's interesting. I mean, I guess that's just the point, right? I'm not actually following the graph there. I'm just clicking on the point. So if I was following the graph, yeah, that's okay. Desmos isn't perfect. Okay, anyway. So I would definitely encourage people to use the tools you have, as long as you're allowed to. Right. So that's one type of thing we can do. And I think I should give you guys the opportunity to do one more question / take a short bathroom break because I have to pee. So I'm going to give you guys one more limit like this. I want you all to work on it and or use the restroom. I'll give you till 9:40. Sure. So find the limit as x approaches -2 of x squared plus 5x plus 6 divided by, sure, 4x squared minus 16. Yeah, go ahead and find that limit. It does exist. It's not undefined. I'm going to use the restroom, and I'll ask you guys your answers approximately at 9:40. All right. So I think the answer is going to be a fraction. I don't know if it's positive or negative, but I would like everyone to type their answer. Don't submit it yet. Everyone type their answer. Give you like 10 seconds to type your answer. All right, I want everyone to submit them. Let me see those answers. Everyone's scared now because everyone's like, we did it wrong last time. It's okay. Wrong answers are good answers. That looks like it could be right. I'm thinking -116 sounds very probable. It's all right if you're not finished too. Let's take a look. So once again, we should always check, is it 0 over 0 before we do anything else? Because if it's not 0 over 0, you don't want to waste your time doing work you didn't need to do. If I plug in -2, on top I'm getting 4 minus 10 plus 6, which is 0. On the bottom I'm getting 4 times 4, which is 16, minus 16, which is 0. Oh, that's all right, Marshall. Sometimes, so that's also a good thing to be aware of, right? It's really important to make sure you write down the original question correctly, because if you write it down incorrectly, you're going to go off in some different direction. So let's take a look. So again, knowing that we have a 0 over 0 means that it's going to have to factor if it's polynomials. And specifically, x minus this number has to be one of the factors. So the numerator has to factor as x plus 2 times something else, and the denominator has to factor as x plus 2 times something else. For the denominator, I might take an intermediate step first. So for the numerator, it's definitely going to have to factor as x plus 2 times, the only other option is x plus 3. Has to be an x here, so the x is multiplied to x squared. Has to be a 3 here, so that 2 times 3 multiplies to 6. And the middle term should work. 2x plus 3x is 5x. We're good to go. In the denominator, before I try and make the factoring work, I would factor out a 4. If I factor out a 4, I'm left with x squared minus 4. And then we can see that the denominator factors as x minus 2 times x plus 2. I might, since I'm limited for space, just erase that and rewrite it instead of writing a whole other step. So that factors as x minus 2 times x plus 2. Alternatively, not that I prefer to do it this way, but if you wanted to, you could probably get the new denominator, holy smokes, the denominator to factor as x plus 2, because we know that has to be a factor. And then the remaining part would have to be 4x minus 8. That's also a way you could do it, which is perfectly fine. It just doesn't seem like the way I would normally think of it. But that's the same, right? X plus 2 times 4x minus 8 is the same as x plus 2 times 4 times x minus 2. So either way, it's fine. Okay, the things that are causing problems, like dividing by 0, are going to cancel. And then we're left with the limit as x approaches -2 of x plus 3 over 4 times x minus 2. Plug in -2, we get -2 plus 3 over 4 times -2 minus 2, which is going to be -2 plus 3 is +1, and 4 times -2 minus 2 is -4. 4 times -4 is -16. So we do get -1/16. And I'm guessing the -5/16 answer came from accidentally adding the 2 plus 3 before making it a negative, but it's really a -2 plus 3. Oh, or okay, yeah, x minus 2 would also get you there. Yeah. So there's your answer. Cool. Let's look at some of the other things we can do. In fact, one of them we already know. Last time, we've already kind of talked about how multiplying by the conjugate is also a method of dealing with specifically square roots. So let's say we had something like, sorry, those is. Let's say we have the limit as x approaches -5 of, let's make it fun, 2x plus 10 over x minus the square root, minus and the plus. Ooh, yeah, let's not be too crazy here. X plus the square root of, I don't know, that, and I'm making something up. Sure, 30 plus x. Okay, as I've said multiple times, let's make sure we actually have to do algebraic stuff before we just start chugging away. So if I plug in -5, the top is going to be -10 plus 10, which is 0. The denominator is going to be -5 plus 30 plus -5 is 25. The square root of 25 is 5. -5 plus 5 is 0. So yes, we do need to do something here. This is a 0 over 0 thing. Which, when you see 0 over 0, you should just think, oh, this isn't the end of the problem. There's always more work to be done if it's a 0 over 0 thing. So here, the work, so there's actually kind of two things at play. The most important thing here is that we need to multiply the denominator by its conjugate. Or more generally, wherever the square root thing is, we have to multiply by its conjugate. So I'm going to rewrite this as the limit as x approaches -5 of the same thing here, x plus the square root of 30 plus x. I might factor out the 2 from the top since it's pretty easy to do. Because we know, or at least we're going to see, we really want an x plus 5 to cancel. Because the x plus 5, if the -5 plus 5 is making it 0, that's what's causing us to have a 0 over 0. We just don't have an x plus 5 in the numerator yet. We can't do anything with the square root until you have a conjugate. So let's toss in the conjugate. This pen could probably stand have some use. Oh, sometimes I like having a trashy pen, but it's a draw graphy stuff, so I'll leave that there. Here's a much better pen. So the conjugate of x plus the square root of 30 plus x is x minus the square root of 30 plus x. So whenever you're talking about a conjugate of a square root thing, the only sign that changes is the one between the non-square root thing and the square root thing. I've definitely seen people accidentally change like this plus sign to a minus sign. That doesn't change. Only this one right there between the not square root thing and the square root thing. Or between two different square root things, if you happen to have like a square root minus another square root. Okay, so this ends up equaling, limit is x versus -5. Here's the other thing you want to know for conjugates. You always want to multiply out the conjugates. So these multiplied out, you get the first thing squared. The middle terms canceled. We're not going to write them. I can show you on the other side if you want me to. You can send me a private message or just write in the chat. James, show me how multiplying out the conjugate really works. But for now, I'm not going to do it unless someone says they want to see it. And then it's going to be minus the second thing squared. So the square root of 30 plus x squared is just 30 plus x. But it is really, really important that it's minus all of it. Right? If you forget these parentheses here, things aren't going to work out the way we need them to. In the numerator, we have 2 times x plus 5 times x minus the square root of 30 plus x. It's also really important to recognize that the things that are not conjugates, we do not want to multiply out. Right? It would be really, really time consuming and not in our interest to FOIL this out. We don't want to do that because we know we want this x plus 5 to cancel. So then let's see what we've got on the bottom. So I'm going to over here just point out that the denominator is really x squared minus x minus 30. And that factors as x minus 6 times x plus 5. What does it say after factor and cancel? Good question. Yeah. We're always looking to cancel the things that are giving us the 0, 0. So really, all of these at the end kind of have a, so even if you're doing the conjugate, you're probably still going to, after that, factor and cancel, like we're about to do here. So this is going to become the limit as x approaches -5 of 2 times x plus 5 times x minus the square root of 30 plus x over, we just said over there that factors is x minus 6 times x plus 5. And look, the x plus 5s cancel out. So then, I hope I have enough room here. I probably do. So now I'm going to plug in the -5, which means I'm not going to write the limit. I'm going to get 2 times, so here I'm going to get -5 minus the square root of 30 plus -5 is 25 over -5 minus 6. And then simplifying that just a little bit, -5 minus 5 is -10. Be careful. I've definitely seen Cuban people say that something like this is 0. Right? -5 minus a number gets more negative, so it's going to be -10. So I've got 2 times -10, which is -20, and -5 minus 6 is -11. 20 over 11. Now let's see here, what else? Sure. So I do think it's good to practice. And how you guys doing? Maybe I can try to do some breakout rooms. Maybe one of these days we'll do some breakout rooms. So I'm going to have you guys try this one. Try the limit as x approaches 4 of 3 minus the square root of x plus 5 over x minus 4. And I will say the things. Definitely a 0 over 0 type. You plug in 4. You get 3 minus the square root of 9, which is 0, and 4 minus 4, which is 0. So you know that you're going to want to multiply this by the conjugate, which is 3 plus the square root of x plus 5 over 3 plus the square root of x plus 5. You want to multiply out the top ones. You want to not multiply out the bottom ones. So go ahead and work on this. I'll give you, I think 90 seconds is a reasonable amount of time to at least start the process. If that is unreasonable, you are also welcome to say, James, that's unreasonable. But let's do 90 seconds. And I'll show you the next step as well. It's very warm in my office. So that's been a little more than 90 seconds, so hopefully that was enough time. Go ahead and type your answer in the chat. Give you 10 seconds to do that. All right, let's see those answers. It might be, I actually don't know. It's okay if you're stuck, it's fun. So if you do get stuck, you don't have to type anything. That's perfectly fine. So maybe it's -1/6, maybe it's not. Let's find out together. -1/6 seems like a pretty good guess, because I'm pretty sure the denominator is going to be 6. Because here's what I know is going to happen before I even do the problem. I know we're going to cancel this x minus 4, because that's what's giving us a 0 in the denominator. And I'm going to plug in the 4 for the remaining x. I'm going to get 3 plus the square root of 9, which is 3 plus 3, which is 6 on the bottom. So I'm pretty sure it's going to be 6 on the bottom. Let's see about the numerator. So it's going to be the limit as x goes to 4 of, what have I got here? 9 minus x plus 5. Note the mistake. Over x minus 4 times 3 plus the square root of x plus 5. And the mistake I made here is forgetting the parentheses, right? If I do this, I have 9 minus x plus 5. 9 plus 5 is 14. I'm not going to get x minus 4. What I really have is 9 minus x plus 5, like that, which is going to give me 9 minus x minus 5. That's going to be, which is just 4 minus x. So this actually brings up something I was saying for the last problem. So here's like I've got the limit as x approaches 4 of 4 minus x over x minus 4 times 3 plus the square root of x plus 5. 4 minus x and x minus 4 don't exactly cancel out. They do, but they leave behind something. So what's 4 minus x divided by x minus 4? Well, as long as x isn't equal to 4, and this is actually an important point, x isn't equal to 4. Right? When you're taking the limit as x approaches 4, you're specifically getting close to 4, but not actually equal to 4. Right? I know we talked about this kind of last class a little bit, but I just want to remind everybody, when you're taking the limit as x is approaching some number, we're getting really, really, really close to that number, but we're not actually ever getting to that number. And again, this expression is really asking you, what is this function getting closer and closer and closer to as x is getting as close to 4 as you want, but not actually equal to 4. So since x isn't equal to 4, what is this equal to? Well, you can either factor out a -1. If I factor out a -1 from the top, I'm left with a -4 plus x over x minus 4, which is equal to -1 times x minus 4 over x minus 4. And x minus 4 is canceled. Another way you can think about it is whenever you subtract things in the opposite direction, they're always negatives of each other. So what's like 2 minus 9 over 9 minus 2? Well, 9 minus 2 is 7. 2 minus 9 is -7. -7 over 7 is -1. And it doesn't matter if whatever the numbers are, as long as they're different numbers, right? 8 minus 91 over 91 minus 8. I'm not exactly sure what either of those are, but I know that this is equal to -1. Always true. When you subtract things in the opposite order and divide them by each other, you're always going to get -1. Because one of them is always the negative of the other. So often what I do when I get to something like this is I say that these cancel, but leave behind a -1. So this is going to equal the limit as x approaches 4 of -1 over 3 plus the square root of x plus 5. And then since we've eliminated the problems, right, the things that were giving us a 0 in the denominator and the numerator, we can then substitute in 4 for the rest of the x's, right? We use the direct substitution property, which just says if you can plug it in, plug it in. And you get -1 over 3 plus the square root of 9, which is indeed -1/6. That's our answer. All right. There is one other algebraic method of trying to deal with 0 over 0 types of limits. And that is the following. Let's look at this one. Sure. Do I want that one? I don't want that one yet. Let me just do this one. Let's do the limit as x approaches 3 of 1 over 2x minus 1/6 over x minus 3. Once again, we can see that this is a 0 over 0 type. If you plug in 3 for x, you get 1/6 here minus 1/6. Clearly 3 minus 3, 0. And in this case, we're going to multiply by a common denominator so that we can simplify things. And there's actually there are two ways of doing this. And I'm going to show you both because one of them I think is a little more easy to kind of see why you would do that. But the other one is easier to actually do the computations for. So normally I would think of this as, oh, well, if I want to subtract these fractions together, I have to have a common denominator. So I need to multiply this one by 3 over 3. I need to multiply this one by x over x. So that I get 6x, right? 6x is the common denominator. I should say it's the least common denominator. You could make a different choice, right? You can multiply this one by 6 over 6 and this one by 2x over 2x if you wanted to, if that's easier to see. So then here's what I've got. I've got the limit as x approaches 3 of, so x minus 3 in the bottom. In the numerator, I'm going to have 3 times 1 over 3 times 2x minus 1 times x over 6 times x. So I can write this as the limit as x approaches 3 of 3 minus x over 6x over x minus 3. And this next step is usually the place where people kind of have an issue or maybe a small challenge. I want to write this as the limit as x approaches 3 of 3 minus x over 6x times, instead of dividing by this, I'm going to multiply by the reciprocal of this. Now, what often happens is people end up just saying it's times this, but it really should be times 1 over x minus 3. Because this here is x minus 3 over 1. And if we're going to flip and multiply, right, multiply by its reciprocal, we should be multiplying by the reciprocal of this, which is 1 over x minus 3. And now we're seeing that same thing that we had in the last problem happen again. 3 minus x divided by x minus 3, right? This is in top, this is in the bottom. These cancel and leave behind a negative 1. So, of course, I run out of room. This ends up equaling the limit as x approaches 3. It doesn't matter if you put the negative 1 in the top or the bottom. I usually put it in the top if there's nothing else in the top. You could write this as negative 1 over 6x. You could also write it as 1 over 6x times negative 1. Doesn't really matter. And then when you plug in the 3, you're going to get negative 1 over 6 times 3. That's your limit. So this is, I think, the easier way to think about this problem. You're like, oh, I just need a common denominator, right? If I'm trying to subtract or add fractions, you always need a common denominator. But let me show you a different way to tackle this problem, just because I think it's a tiny bit easier. And then we'll do another one. And then we'll talk about, I guess we'll talk about some limits that end up being infinite. Let's see. What do I want to say? Okay, same limit. Limit is x approaches 3 of 1 over 2x minus 1 over 3, sorry, 1 over 6. So now, another way you can do this is instead of saying I'm going to get a common denominator, I'm going to multiply everything by that common denominator. So the common denominator of 1 over 2x and 1 over 6 is 6x, not 1 over 6x. So I'm going to multiply by 6x. But of course, we're not allowed to multiply by just 6x. We're really only allowed to multiply by 1. It's the only thing you can multiply by that doesn't change stuff. So we're really going to multiply by 6x over 6x. And then we're going to distribute here. So the limit as x approaches 3 of 6x times 1 over 2x. Things cancel and we're left with a 3, right? 6x divided by 2x is 3. 6x times 1 over 6, the 6 is canceled and we're left with x. And then in the denominator, we're not going to multiply it out, right? Just like when you're multiplying conjugates, you multiply out the conjugates and you don't multiply out the parts that aren't conjugates. Same deal here. If you're multiplying by a common denominator, you multiply out the part that has the denominators and you don't multiply out the part that doesn't cancel stuff. So the bottom is going to be x minus 3 times 6x. And then the 3 minus x over the x minus 3 cancels and leaves behind a negative 1. So we're going to get the limit as x approaches 3 of negative 1 over 6x, which again is negative 1 over 18. How did they get the 6x? That's an excellent question. That is the part of doing it this way that is less intuitive. So let me go back to the other side for 1 second. So here, I subtracted these together by getting a common denominator, right? I saw that 6x was the common denominator, and I multiplied this one by 3 over 3 to get a 3 over 6x, and this one by 1 over 6 to get an x over 6x. But, so this is one way of doing it. However, this, right, it's a lot of steps. It's a little bit messy. What we can do instead is say that, oh, I see that the common denominator is 6x. You could have picked a different one. You could have picked 12, right? Any common denominator will work for this. So if you would prefer, we can do it again, but pick 12x if it's easier to see that 12x is the common denominator. But I said, oh, 6x is the common denominator. So that I know that if I multiply a fraction by its common denominator, it's going to cancel out the denominator. So that's what I did instead. I picked 6x because I knew it was the common denominator, and then multiplied it by these fractions to get rid of the denominators. It would also have worked if we picked 12x or anything that was a product of these two things and then any other number. Let's do another one, and let's do it kind of the fast way, meaning the less intuitive but much more calculation, less intensive. The words are really coming to me today. Let's try another one. So let's say we wanted to find the, where'd you go here? Limit as x approaches 5. So it's a little more work of 1 over x plus 2 minus 1 over 7 all over x squared minus 25. So I will again point out, we could get a common denominator by multiplying this fraction by 7 over 7 and this fraction by x plus 2 over x plus 2. Actually, before I do that, let's rewind. Do I need to do any of this work? Is this really even 0 over 0? Yeah, it is. If I plug in 5, I get 1/7 minus 1/7. If I plug in 5, I get 0. So yes, it's 0 over 0. So instead of multiplying this by 7 over 7 and this by x plus 2 over x plus 2, I'm going to multiply the entire thing by that common denominator, by 7 times x plus 2. And I'm really just picking that because it is the common denominator of these two fractions. That's how we choose it. So then we're going to multiply out or distribute, if you prefer that word. We're going to distribute to the fractions so that the denominators cancel. The limit is x approaches 5 of, so 7 times x plus 2 times 1 over x plus 2, the x plus 2's cancel, and we get a 7, minus 7 times x plus 2 times 1/7, the 7's cancel, and we get an x plus 2. Now be careful, it has to be minus all of x plus 2. The denominator, I don't want to multiply this out, right? So let me ask you guys, without looking at any of what I've written, if you just look at the limit as x approaches 5, what kind of factor do we know we need to cancel out? We want to cancel out an x minus what? Right. We know we're trying to cancel an x minus 5. So that means I want an x minus 5 to show up. specifically, I want to factor this as x plus 5 times x minus 5. And I don't want to multiply this out. It's no help. I'm just going to leave it as x plus 2. And now the numerator is looking like 7 minus x minus 2. So this is looking like the limit as x approaches 5. 7 minus x minus 2. 7 minus 2 is 5. So I'm getting a 5 minus x over x plus 5 times x minus 5 times 7 times x plus 2. I didn't really mean to put parentheses around 7, but I wrote them under there. And then the 5 minus x and the x minus 5, those cancel out and leave behind a minus 1, since they're subtraction in the opposite order. And now I've got the limit as x approaches 5 of minus 1 over x plus 5 times 7 times x plus 2, which ends up being negative 1 over 5 plus 5 times 7 times 5 plus 2, which is 10 times 7 times 7, which is 10 times 49, which is 490. So negative 1 over 490. And I will point out, I think this is computationally much, maybe not much, but certainly it is less computationally difficult than if I was to do 7 over 7, x plus 2 over x plus 2. And then it just, then you have, doing it this way immediately eliminates the fractions in fractions, which is just less terrible to write. So I would encourage you all, if you're doing one of these 0 over 0 types of limits and you are trying to get a common denominator because you have fractions and fractions, it is usually easier to do it this way, where you multiply the top and the bottom by this or this. The 7's there. Oh, do you mean this 7? So what I did here was I had 7 minus x minus 2, and then the 7 minus 2 became 5. So if you have a 0 over 0 type of limit, most of the time, with a couple exceptions, these are the three things you want to look to do. You want to look to do some algebra, meaning you can factor and cancel, or if there's a square root, you can multiply by the conjugate, or if there's some fractions, like fractions and fractions, you can multiply by a common denominator. There are two other, at least to my mind, types of 0 over 0 limits that don't kind of allow for this. One of them, I don't think I don't know. So I'll talk about both of them right now. And I guess we'll have to wait until Tuesday to talk about. Yeah. Well, I'll talk about one of them. So actually, let me ask you guys first of all, have either of your classes talked about this type of limit? The limit as x goes to 0 of sine of x over x. Any yeses on that? No. Cool. Great. We'll save it for Tuesday. Someone writes yes. Usually that limit comes a little later in 16a. So, but the other type of limit the other type of 0 over 0 limit that you might have seen is something like this. The limit as x approaches 5 of the absolute value of x minus 5 over 2 times x minus 10. 2 times, oh my God, without the parentheses. So there's the limit for you. And the issue here is that, well, it's a 0 over 0, right? If we plug in 5, you get 0 on top and 0 on the bottom. And in this case, you can't just factor and cancel. You can't just drop the absolute values because the absolute values have meaning. And the meaning of an absolute value is that, well, here's what I'll say. I know that the absolute value of x minus 5, this is equal to, oh, wow, that's good. So here's what I always think about for an absolute value. An absolute value is equal to whatever's inside if the inside stuff is positive. So the absolute value of x minus 5 is equal to x minus 5 if x is bigger than 5. On the other hand, if the inside stuff is negative, then to turn a negative number into a positive number, you have to multiply it by -1. So we're going to multiply the inside stuff by -1 if the insides happen to be less than 5. or sorry, if the insides are negative, which means if x is less than 5. So for example, hopefully you guys can read this all right. I feel like I could have written that a little bit better. Let me try it one more time. Let me just, yeah. So the absolute value of x minus 5 is equal to x minus 5 if x is bigger than 5, and is equal to the negative of x minus 5 if x is less than 5. So for example, if x was 7, the absolute value of 7 minus 5 is 7 minus 5, which is 2. If x was 1, the absolute value of 1 minus 5 is negative 1 minus 5. 1 minus 5 is negative 4. Negative 4 is positive 4. So an absolute value always takes the insides and turns it positive, no matter what it is. Well, I'm trying to figure out what happens as I approach 5. And the problem is there are two sides of 5. There's the right side of 5 and there's the left side of 5. So the right side of 5 is the stuff that's bigger than 5. The left side of 5 is the stuff that's less than 5. So if I'm trying to find the limit as x approaches 5, I'm going to look at the limit from both sides. So look at the limit as x approaches 5 from the right. Well, if x is bigger than 5, then the absolute value of x minus 5 is just x minus 5. So I can say this is the limit as x approaches 5 from the right of x minus 5 over, I'm going to factor the denominator as 2 times x minus 5. This part cancels with that part. We're left with the limit as x approaches 5 from the right of 1 over 2. And the limit of a constant is just the constant. Right, there's nowhere to plug in x, so we just get 1/2. On the other side, if I look at the limit as x approaches 5 from the left, so I'm less than 5. Well then, if x is less than 5, then the absolute value of x minus 5 is equal to negative x minus 5. This is going to be the limit as x approaches 5 from the left of negative x minus 5 over 2 times x minus 5. And if I cancel the x minus 5's here, I'm left with the limit as x approaches 5 of negative 1 over 2, which is negative 1/2. So here's what this means. It means that the limit from the right and the limit from the left have different values. And if the left-hand limit and the right-hand limit aren't meeting up, that means the overall limit doesn't exist. So we can say that the limit as x approaches 5 of the absolute value of x minus 5 over 2x minus 10 does not exist. Wow, I can spell. Which is often abbreviated as just DNE. So typically, when you're dealing with a limit that's involving an absolute value, you almost always have to break it up into a left-hand side limit and a right-hand side limit and see if they're equal to each other or not. And most of the time, they are not equal to each other. Also, you can graph something like this if you want to, right? Just to kind of show you guys. So graphically, so I know I've kind of said this a couple times. I'll say it one more time. I really think graphing things. Yeah, good question. So someone asked if the limit would have been 1/2 for both, it would exist, right? So yeah, that's a really good point. In fact, so the graph, not super important. The graph just looks like negative 1/2 on the left and positive 1. So in fact, I don't need to. I can show you the graph. I can actually just draw it faster than I can probably do that. So yeah, the graph of that function looks like this. Undefined at 5, and then here's 1/2. There's negative 1/2. It looks like it's always equal to 1/2 to the right. It's always equal to, sorry, put that 5 in the wrong spot. It's always equal to negative 1/2 to the left. And it's not defined to be anything there, right? If you look at this over this, it's obviously undefined at 5. But yeah, so someone asked a question that I think is worth addressing. So if the limit as x approaches a from the left-hand side of f of x is equal to the limit as x approaches a from the right-hand side of f of x. So if the left-hand limit is equal to the right-hand limit, then the overall limit always exists. Then the limit as x approaches a of f of x and is equal to whatever those are equal to. So typically we actually say like, if the limit as x approaches a from the left equals the limit as x approaches a from the right equals some value L, then the limit as x approaches a overall exists and is equal to L. So yeah, that's often what we're doing when we're checking to see. This also has to do with continuity, but so later on, like probably next week, when we talk about continuity, one of the conditions for a function to be continuous is that the limit exists, and often involves checking that the limit from the left-hand side is equal to the limit from the right-hand side.